Hello and welcome back to Honors Topics in Physics. Today we're continuing our discussion of momentum with conservation of momentum. And this is very similar to conservation of energy in that it means that however much momentum you start with is the amount of momentum that you end up with in an isolated system, that is. So let's look at an example with a cannon and a cannonball. So if I have a cannon and a cannonball, initially both their momenta is 0, okay, and then after they fire, the cannon has some momentum to the left, and the ball has some momentum to the right. So which object changes momentum after firing? Both. Okay. So what does it mean when we say that momentum is conserved? We've already kind of talked about that. Let's look at it from Newton's third law standpoint. So which during the firing process, which has the greater force on it, the cannon, the ball, or is it the same? Well, Newton's third law says that there are equal and opposite forces, so it is the same. Okay, which of those is going to have the force on it for the longer period of time, the cannon, the ball, or would it be the same? Well, it'd be they can only push on each other for the exact same amount of time. They're pushing on each other, so that is the same. So if they both experience the same force for the same time, that means they both experience the same impulse. And remember from before, impulse equals the change in what? Impulse equals the change in momentum. So if they both have the same impulse, that means they both have the same change in momentum. So if they both start out with 0 momentum, and they both have the same change in momentum, who's going to end up with more, the cannon or the ball? Okay, well, they're both going to end up with the same amount of momentum. The cannon itself has a large mass but a small velocity. Okay, the ball has a small mass but a much larger velocity. So it ends up that's how they both have the same amount of momentum after firing. Okay, now there is something different about the momentum other than just the fact that the cannon's got a large mass and the ball's got a small mass but a larger velocity. That is the direction of their momentum. And how would we talk about the different directions? What do we do on a number that's got a different that has a direction to the left or to the right? We're talking about signs. Okay, so let's say that the cannon or the ball ends up with +5 units of momentum to the right. Then the cannon is going to end up with -5 units of momentum. Okay, meaning to the left. Okay, so what do we get if we add up the final momentum? We get +5 plus -5 gives us 0. Okay, the initial momentum of the cannon and the ball was 0. Okay, because they were both at rest. And then when we look at it after firing, and we add up the momentum of the cannon and the ball, we also get 0. So that's what we mean by the total. That's what we mean by saying momentum is conserved. That we started with 0 and we ended up with 0 when we add up the pieces. Okay, so now there is a caveat to that. Okay, the momentum is conserved if there's no external force. Okay, if nothing outside of our system, okay, which is the cannon and the ball, okay, if nothing exerts a force on our cannonball system, then the momentum doesn't change. And by saying it doesn't change, we mean initial momentum equals final momentum, or putting that in terms of math, P1 equals P2. Okay, so our system that we're interested in is just the cannon and the ball. That's what we're looking at. Anything outside of our cannon or ball system is considered an external force. So if we had a big truck come along and bump our cannon ball system, okay, it's going to change the momentum. So momentum would not be conserved in our cannonball system. Now, if we included the truck in our system, then it would be conserved. Okay. What about friction? Would friction be an external force? Okay. Well, it would be because the friction is caused by the earth, and the earth is not part of our cannonball system. So friction, that's what causes the cannon to lose its negative momentum and come to a stop. And okay. So does this mean, by saying that the initial momentum equals the final momentum, does that mean that the momentum of a particular piece cannot change? Or does it mean that the total momentum doesn't change? It means that the total momentum doesn't change. So let's look at an example. We've got Jack and Jill. Jack and Jill are at rest. They're on roller skates, and they're facing each other, and they're going to push off of each other. Okay, so initially they're at rest. Okay, after they push off, Jack is moving at plus 10 meters per second, and we want to figure out what Jill's velocity is. Okay, well, what we want to do is look at the initial momentum of Jill, the initial momentum of Jack, and set that equal to the final momentum of Jill and the final momentum of Jack. Okay, the initial momentum of Jill is 40 times 0. Her velocity is 0. Okay, her mass is 40 kilos. So that is 0. The initial momentum of Jack is his mass times his velocity, which is 80 times 0. So the initial momentum is 0. Okay. Now, on the final piece of the puzzle here, we've got Jill's velocity. We want to figure out what Jill's velocity is. We know her mass is 40. So her mass times her velocity is going to equal Jack's momentum. Or it's going to equal, in this case it is, just it's going to be opposite sign. We're going to add to that Jack's momentum, which is his mass times his velocity, which is the 10 meters per second to the right. And when we solve that, we get that Jill's momentum is equal, or Jill's velocity is negative 20 meters per second. Okay, and what does the negative mean? It means she's traveling to the left while he's moving to the right. And isn't that what would happen if they pushed off of each other on roller skates? Jack would move off one way and Jill would move off the other way. Okay. So let's say we've got another cannonball system here. Let's look at another example. We've got the cannonball moving to the right and the cannon moving to the left. We've got a cannon of mass 650 kilograms, and the ball has a mass of 25 kilograms. Initially, everything's at rest. Okay, it's loaded and ready to fire. After firing, the ball flies out at 35 meters per second to the right. What's the velocity of the cannon? I think it's helpful to draw a picture with these, and you've got your initial picture, and then you've got your final picture. So initially we've got our cannon and a ball, and they're at rest, okay, and our initial momentum is going to be 0 of our system, okay, and then over on the right side we're going to have the cannon moving to the left and the ball moving to the right. Okay, so our initial momentum has to equal our final momentum. So the cannon's momentum is going to equal 650, its mass, times the velocity, and that's what we're trying to find. Okay, and then the momentum of the cannonball is equal to its mass, which is 25 times 35. Okay, and when we solve, okay, we get that the velocity of the cannon is equal to negative 1.35 meters per second. So all we did was say our initial momentum equals our final momentum. Okay, so what we've looked at are what we can consider explosions, where things are initially at rest and then things go flying apart. Okay, so just like our cannon and our ball, so you think of it an explosion, or Jack and Jill pushing off from each other, very similar. Next thing we want to look at is conservation of momentum in collisions. And just like before, the initial momentum is going to equal the final momentum, but the initial momentum is not going to be 0 in a collision, okay, because something's got to be moving in order to hit something else. And there's two basic types of collisions. There's elastic collisions, where objects hit and they bounce off of each other and no energy is lost. Okay? And there's inelastic collisions, where objects hit and they stick together and will always lose some energy in that type of collision. Okay? But it doesn't really matter as far as conservation of momentum goes. Momentum will always be conserved in any type of collision. Okay, as long as there's no external forces. Okay, so let's look at a few of these collisions on a air track simulator. So let's look at an elastic collision where they both have the same mass, and we've got one object moving, which is going to be the red. So here comes the red, and it transfers its momentum. So because momentum is conserved, all that means is that momentum gets transferred from one object to another object. That's all that goes on when we've got a collision, is momentum is transferred from one object to another object. You can think of momentum as like money. The money is spent and it goes from one store to another store, kind of like energy, but it's got to show up somewhere. Okay, let's make one car more massive. Let's make the the blue car more massive, twice the mass. Close enough. So, and because the blue was more heavy, was more massive, the red rebounded and took off. Let's make the red more heavy. Okay, and we'll close enough. I think it's interesting that the blue car takes off at a faster speed than the red car when during that collision. I don't know. To me, that just is kind of interesting. It's cooler to see in real objects. So those were elastic collisions. Let's look at some inelastic collisions. Let's say we've got. Let's move this car down to 0. Okay, so now we've got a car that's at 100. And now notice when they hit, they both move off at 50. That's because they're sharing the same amount of momentum but have twice the mass, which means the velocity needs to be cut in half. So originally it was one was at 100 and the other one was at 0. So anyway, it's sharing the momentum between the two objects. Let's do a heavier car. Let's have a lighter car hitting the heavier car. And we'll see. So here we've got a heavier car. Now notice that it really slows down here. And in fact, the velocity is approximately a third of what it was before. And that's because the mass increased by a factor of 3, and then keep the momentum the same, the velocity decreased by a factor of 3. So that is that. Okay. There's Newton's cradle applet. You guys have, I'm sure, seen one of these, if not in person, in some kind of video. These are pretty cool. I've got a real one at school, but we're not at school, so you can't see it. So we're going to have a collision where we have 1 unit of momentum. We're going to have 1 unit of momentum is going to impact these other balls. Okay, and then out pops another one. This one comes to a stop. Okay, that momentum is just transferred from one ball to another. The total amount of momentum stays the same, but momentum is transferred from one object to another object. Okay. Now, if I start with 2 units of momentum, okay, then I'm going to have 2 units of momentum pop out the other side. Okay, and again, that total amount of momentum is conserved; it remains constant. Although these aren't perfectly elastic collisions, so we'll lose some energy to heat and some things like that. And if we have, what I think is cool about this one is the fact that the green one never moves; it just stays put. And if we start with 3, then we'll have 3 units of momentum pop out the other side. If we start with 4, bloop, bloop, and the best is 5. Check this out. I know, isn't that amazing? How do I do this? I must be a wizard. So anyway, that's my Newton's cradle applet. Let's work a couple problems along with this. Let's see, we've got a 4 kilogram car moving at 15 meters per second. Okay, so here's our 4 kilogram car moving at 15 meters per second. It hits an 8 kilogram car at rest. Okay, so here's my 8 kilogram car at rest, 0 meters per second. What is their velocity after they hit and stick together? Okay, so we're going to say my initial momentum equals my final momentum. Okay, so my mass times velocity, 4 times 15, plus 8 times 0 for this guy, 8 times 0, equals, now they're going to hit and stick together, which means they're going to have the same velocity, which means we can consider them one object. Okay, so we're just going to look at it, instead of having a separate 4 kilogram and a separate 8 kilogram, we're just going to say we've got a 12 kilogram object. And what we're trying to do is figure out the velocity afterwards. Okay, so so we solve this and we get that the velocity equals 5 meters per second. Now, if we look at this, my mass, my moving mass, goes from 4 to 12, which means it increases by 3. and my mass increases by a factor of 3, and my velocity decreases by a factor of 3 in order for the momentum to remain constant. So you can play ratio games with this. Let's say we've got a hobo. He jumps into the back of a moving truck moving at 14 meters per second. Assuming the hobo has no initial momentum, what's the final speed of the truck and hobo? It's a very heavy hobo. It must be pretty agile jumping into the back of a moving truck. So I do not have a picture of a hobo and a truck. I'm sorry. I should have drawn one. So the hobo has an initial momentum of 0, 210 times 0, plus the initial momentum of the truck, which is 670 times 14. This is my initial picture. What's the final momentum, or what's the final velocity of the truck and the hobo moving off together? So I added the mass of the truck and the hobo together to get 880. And we're looking for the final velocity. So solving this, I get 10.7 meters per second. Okay. Last problem. This one has got a little bit of a trick to it. So we've got a 3 kilogram car moving to the right at 5 meters per second. So here's my 3 kilogram moving to the right at 5 meters per second. I forgot to put an arrow. Hits and sticks to a 6 kilogram car moving to the left at 2 meters per second. Okay. So here's my 6 kilogram moving to the left at 2. Okay. What's the final velocity of both of them after the collision? So they hit and stick together. So what we've got is 3 times 5 for my initial momentum of the first object, plus 6 times minus 2. You can't forget the fact that this velocity is negative, because that completely changes your answer. The fact that this is negative. Okay, so I've got some initial positive momentum and I've got some initial negative momentum. Okay, and that's going to be that's going to equal the two sticking together, the momentum of that. So that equals 9, which is our total mass on the right side. Okay, the 3 plus the 6 times the velocity, which is unknown. So when I do the math, what I get is that v is equal to 0.3. Okay, and that's an example where you've got an object moving to the right and an object moving to the left. So keep track of those directions. That's important. And then what I want you to do is work on worksheet 5-2. And if you have any questions, see me in office hours.